So hello and welcome to the Azure Global 2022 in Lüdinghausen. I'm very happy to speak about this interesting topic of quantum computing on Azure Quantum. I agreed with the organizers of the meetup that I'll do this presentation in English. Should you want to have a German version of that, then just let me know and we will find an alternative. But let's dive in. My name is Holger Sirtl. I'm a cloud solution architect and quantum ambassador at Microsoft, and I'm working on the interesting topic of quantum computing. And in this presentation, I would like to answer a few questions. The first one, why do we need a new way of computing? What is so wrong with classical IT, which is quite mature? Why do we need a new way of computing? How is quantum computing different? And then, of course, I'll have a look at what Azure Quantum provides in that context. And at the end, I'll give you an outlook and some hints and tips what you should do when you want to dive into that topic, quantum computing in general and Azure Quantum. So why do we need a new way of computing? We all know this law, Moore's law, which says that every 2 years, the number of transistors on our computer chips doubles, which means that it is foreseeable that we have more and more compute power at our hands. And the question is, why can't we wait for maybe 1 or 2 years to have enough compute power to do new things, new exciting things? What is wrong about this Moore's law? The first one is that Moore's law, and some scientists say that it won't be maintainable forever. So even with the classical IT, we come to an end of that evolution. And on the other hand, we see as Microsoft, and you see it also in public media, that nowadays we are facing challenges, compute challenges involved with digital transformation, with sustainability, environment protection, and so on, that we have a growing number of problems that aren't tractable with classical IT. They have exponential resource requirements, or are NP complete, for example, meaning that with growing complexity of these problems, the resource requirements grow exponentially. And what that means, I will illustrate in the following picture. Here you see, illustrated, let's say, chemistry simulation. So let's say I want to simulate molecules consisting of a number of atoms. And the problem with the simulation challenge is that with the number of atoms, the resource requirements to simulate the molecule behavior grows exponentially. That means that this curve that you see here is very, very steep then at the end. And at a certain point or number of atoms, we require more resources classically that are available. And the compute time I would need to compute this problem would be longer than the age of the universe. And this should illustrate that we come to a barrier where we cannot, and where it is mathematically provable that we cannot compute certain things. We can hope that this curve moves a little bit to the right. I reference again to the Moore's law, where we say, okay, in future we might have more powerful PCs at our hands, and with cloud computing, everyone can access really huge amounts of resources from the cloud. So there might be some classical innovation that moves this curve a bit to the right, but it still won't be sufficient, and there still will be this barrier of problems that we cannot compute with classical IT approaches. And quantum computing now promises to move this curve in a different direction, promises to bring exponential speed up for a certain type of problems. And this type of problems are those problems who have exponential runtime requirements or exponential complexity. And with quantum computing, the promise is that we can calculate lots bigger molecules, for example, in chemistry simulation or in other scientific areas. One important thing here is the so-called crossover size and crossover time, which means there is a certain point where quantum computing can actually bring this advantage. Up to a certain size of problem, we can say that the classical classical systems are mature enough, fast enough that we can do the calculations on these classical systems, and we don't need to wait for quantum computing to bring that. But there's certain size and time where quantum computing brings a benefit. And to decide whether quantum computing is a promisable approach, we should have a close look at crossover time, for example. So if the crossover time is, let's say, a year, so where we say with classical computing, we would have to calculate 100 years, and with quantum computing, we can calculate the problem in a year, then this is probably not the problem that we should look for, because a year is still very, quite a long time. So we need to have a problem where the crossover time and crossover size of the problem is of interesting characteristic. So how does quantum computing achieve this advantage to a classical IT? And for answering this question, I'd like to show you a quote of Richard Feynman, a theoretical physicist, who made this quote here: "Nature seems to be able to efficiently simulate itself." So what does it mean? It means that nature, if you want to simulate a molecule, the easiest way to simulate it is to take the molecule and let it behave, let's say. So nature does the simulation intrinsically. So since nature behaves like that, how can we use the effects that nature uses to simulate itself, maybe in computing systems? So maybe we can use quantum mechanical effects in computers. And this is the key for understanding what quantum computing actually is doing. It uses quantum mechanical effects. And for understanding these effects, I would like to show you a few of them. Don't worry, I'll abstract a bit from a big physical lecture and make it as easy as possible. And for making it as easy as possible, I would like to show you or have a look at the smallest unit of compute that we have in classical IT. And the smallest unit is the classical bit. A bit, everyone knows, is either 0 or 1. It's on or off. The light bulb here, what we see is either on or off. So at each point in time, a classical bit can only hold 1 bit of information. And this is important and is as trivial as it sounds, this sentence. So at each point in time, only 1 state is the key for understanding how quantum computing is an advanced approach here. Imagine you have an optimization problem, or you have a problem where you need to calculate lots of alternatives, and you're looking for one specific one that has certain characteristics. With classical IT, you would have to calculate one after the other, because the classical IT system at a certain point can only hold one alternative. Of course, you can use parallel computing and things like that, but for each unit of the parallel computer, the same is true. It only can hold one certain state at a given time. And to illustrate this even more, I would like to go to this maze here. You have this bullfighter in the upper left corner here and the bull in the middle. And the question is, what path leads to the bull here? With classical IT, the approach would be that you calculate each alternative way one after the other, And then at a certain point in time, you have luck and you find the solution, the way that leads to the bull. If you're lucky, it's right the first attempt. If you have bad luck, then you maybe calculate all, and it's the very last option, like Murphy's law. It's the last option that you look at. That's the one that you're looking for. If we go back to the bit, quantum computers are not using classical bits, but qubits, quantum bits. And the advantage of a qubit is that it can hold multiple states at the same time. This is an abstracted view. What's really happening here. In fact, a quantum bit, a qubit, holds a linear combination of these base states. You have the formula here below the light bulb, alpha 0 plus beta 1. That means that it's a linear combination of 0 and 1. Since it can hold two states at the same time, a quantum computer can calculate lots of alternatives in parallel, with the ability that it can hold multiple states at the same time. And imagine if you have not only one qubit, but multiple qubits. 2 qubits, for example, can hold 4 states at the same time. So it's always 2 to the power of n and the number of qubits, the states that can be held in a quantum computer at a certain time. This means that with quantum bits, with qubits, if you wanted to simulate them on a classical computer, the resource requirements would grow exponentially. For simulating a qubit, a single qubit, you would need 2 classical bits. 2 to the power of 1 is 2, so 0 and 1 if you want to hold these states. For 20 qubits, you would need 16 megabytes, which is not very much. For 30, 16 gigabytes. So even your laptop computer might be sufficient for simulating 30 qubits. 40, you are already in very large virtual machines, maybe in the cloud. 50 qubits, you might need a whole data center to simulate that, because you would need 16 petabytes. But if you go to a number like 260 qubits, for example, then you would need more bits than there are atoms in the visible universe. And this shows you that at a certain point, you won't have enough classical resources to simulate and do what the quantum computer is capable of. Nowadays, we can say about 52, 53 qubits, this is simulatable, but above this barrier, it's no longer simulatable. You need to do some tricks to simulate more than that, but it gets so complicated that it's probably easier to actually build quantum computers with more qubits. So you would say, okay, a quantum computer can do this in parallel. Why not put all my classical algorithms on a quantum computer and just do it in parallel and everything's fine? There's a little flaw in the whole concept, and this flaw is not little. It's actually it's the one of the main challenges of quantum computing, because the problem with qubits is you cannot look at a qubit, a physical qubit, and look what its current state is. You cannot see whether it's 0 or 1. If you want to measure the state of a qubit, you actually have to measure it. And measuring means that it will collapse to a so-called base state, 0 or 1. Yeah? So measuring, looking at a qubit, disturbs the qubit and makes the qubit collapse to a classical state. And these 2 parameters that we have to describe the state of a qubit, alpha and beta, they determine what the probability is for measuring either 0 or 1. It's always the number alpha, for example, alpha squared is the probability of measuring 0 or 1. So this is one of the challenges. And going back to our sample with the maze that I showed you here, a quantum computer can calculate all these options at the same time. But if you would measure it right away, then you will get any of those results, which doesn't give you really an advantage. And the art of creating quantum algorithms is to manipulate the states of the qubits in a way that the desired solution is the one that you would measure at the end with the highest probability. So you want to tune the state of this quantum system so that the blue line, the one that actually leads to the bull in the middle, is measured with highest probabilities. So you eliminate all the other options. And how do you manipulate these states? This is done by so-called quantum gates. The quantum gates are very similar to the classical gates that you know, the NOT gate, AND gate, OR gate. Similar gates exist in the quantum world, but the difference, or the main difference, is that they can deal with superpositions. And another difference is that they are all reversible. This means that you can use quantum gates to transform a qubit from one state into another. And the goal is then to tune it in a way that you get the desired result. So if we look at quantum algorithms on a very high abstraction level, they all have the same structure. You have an initialization phase. In this initialization phase, you say how many qubits you want for your algorithm. Then you let these qubits interact with each other. You do this by applying gates on them, so they influence each other. And then at the end, you're doing a measurement. So these three phases, initialization, state evolution, measurement, these are the phases that all quantum algorithms have in common. So in our example, typically, you would put the qubits in a perfect superposition. So if you would measure it at that point in time, you would measure any of those results with equal probability. But the art is to let the quantum computer do a state evolution in a way that it promotes the desired result in a way that this gets measured at the end with highest probability. So in our case here, the 0, 1, 0 state is the one that you would measure with 99.9% probability or so. So you would measure that at the end. So to sum up, these are the quantum effects that I showed you. It's first the superposition. This is the one that gives the real power to quantum computers, the ability of calculating many options in parallel. Then the quantum gates to influence the state in a way that the desired result will be measured with highest probability at the end, and then at the end, the actual measurement. And the measurement is the thing that makes quantum computing actually very hard, because you only get one result back. And because of the probabilistic nature of quantum computers, you always have these, you measure it, and only with a certain probability you get a certain result. You should run your algorithms multiple times to verify that actually the result you measured in the first attempt is actually stable and will be measured at subsequent steps as well. So I hope this gives you a picture of what is the power of quantum computers and what are challenges in quantum computing. And now the question is, what is Microsoft doing in that space, and how can I work with all that? How can I actually use a quantum computer, for example? Quantum computing at Microsoft is quite old. For about, I think, 15 years or so, we are working together with research institutes around the world. We have 3 in US, we have 4 in Europe, and 1 in Australia. And we are working with these research institutes on all levels of quantum computing, starting from the QPU, the quantum processing unit, to bring out a first-party hardware in the future, up to compilers, programming languages, programmer support, and so on, and all the hardware around the quantum processor. We have an Azure Quantum, so-called Azure Quantum network, where we work with partners and also research and educating organizations together to promote the topic, to create industry solutions that are ready to use, samples that you can use to create your own solutions. And this Azure Quantum network is growing every day. We have on board new partners. If you're interested in doing that, then have a look at the Azure Quantum documentation pages. For enterprise customers and for partners, there's a similar program available. We have a so-called Enterprise Acceleration Program, where we directly work with enterprises on specific problems and challenges that they have, proof of concepts, for example, and work together with them to develop quantum algorithms that then can be used in production scenarios. Our benefit out of that program is that we improve our own service and see if there are certain patterns that are frequently required and might be where it might be reasonable to build these into the service. We have a quantum development kit. This is an open source toolkit that you can download for free. This includes developer tools, libraries that you can use to start coding in your favorite programming language, whether it's Python or Q# or any other language. And whether you're programming in Visual Studio Code, Visual Studio, or Jupyter Notebooks, everything is supported here. We have simulators in that toolkit as well. So up to a certain degree, and you've seen the exponential growth of resource requirements, to what degree you can actually simulate. These simulators are available, and this is only basically limited by the size of the RAM of your laptop or your local machine, what you can simulate there. On a typical laptop, I would say you can simulate up to 30 qubits maybe, and do your experiments there. The advantage of a simulator is that you can actually look at the state of the simulated qubits. I mean, they are not real, they are simulated. So you can look at the classical bits that represent the qubits and see what the status is. So you can debug step by step through your code before you submit your quantum job then actually to the quantum environment and physical hardware. And this physical hardware is made accessible via the Azure Quantum service. This is the heart of our offering. The Azure Quantum service is a fully managed service. So you provision the Azure Quantum service, and then you have an interface, an API that you can access to run your quantum algorithms on physical hardware. And we are working together with several hardware providers like IonQ, 1QBit, Rigetti, Quantinum, Pascal came very new to the family, QCI, and so on. We have our own providers that are made available through the Azure Quantum service. One of our goals is that to make it as hardware agnostic as possible. So you should be able to write your quantum algorithms and decide at a very late stage in your development on what hardware you're running that. You can actually go there and submit your job, your quantum job, to several different hardware environments and compare the results that come out or the runtime behavior that you are seeing there. Very important, the second point here on the left, on the right, you get $500 free credits, and this is working also with free Azure accounts. So if you don't have an Azure account and you don't have any money, so to say, to spend, then you still can create a free Azure account and then provision an Azure Quantum workspace, and you get $500 free credits. So you don't have to pay anything to actually work with physical quantum hardware. And for larger projects, you can fill out an application form, and then you can get up to $10,000 worth of quantum compute time on our partners' hardware. If you have already experience in different quantum offerings, like if you have experience with IBM Qiskit, for example, or Google Cirq, you can bring in your algorithms that you developed on those platforms and run them on Azure Quantum as well to submit your code to maybe different hardware environments. So this is a very important cornerstone of our offering, that we want to pick you up wherever you are. Let's say what your experience is, you can reuse them on Azure Quantum. On an architecture level, the whole service looks like the one that you see here on this picture. Basically, if you provision Azure Quantum, you provision a quantum workspace. The workspace is the service or the entity that you provision on Azure that you can submit your quantum jobs to. Typically, you write your jobs on any development environment like Visual Studio Code, command line, Jupyter Notebooks, wherever. You can automate the submission process even with DevOps tools like Azure DevOps or GitHub. And the whole service integrates fully into other Azure services. For example, if you want to get notified if a quantum job completes, then just use Event Hub and connect it to a Logic app, for example, to send out emails or do whatever post-processing that you would need. Azure AD can be used to do the authentication authorization process around Azure Quantum, so not everyone can submit code or jobs, but only dedicated resources. So let's have a look at how provisioning Quantum actually looks like. And for that, I'm quickly going to the Azure portal. And the portal moved to another screen. Here we have the Azure portal, and you provision Azure Quantum the same way like you would do with any other Azure service. You go to create a resource, and you can search for Azure Quantum and say you want Azure Quantum, click on Create. And then you have two options, either Quick Create. Quick Create will create a default resource group with a fixed name, and every naming is in a standard way, which is the fastest way, of course, of provisioning. I'll go to the Advanced Create because I want to explain a few facts about the Azure Quantum service. First, I need to specify the resource group. The subscription is the one that I'm logged into. So I can say, okay, meetup RG will be my resource group. Then I need to give a name to my workspace. Meetup WS. And then I need to specify a region. Specifying a region here only has effect on where the workspace is located. It doesn't influence where the hardware is that you would submit your job later. With the exception of Pascal, all the quantum environments that we are offering are currently in the US based. We are very aware of the requirement that people want to access quantum resources closer to their home base in Europe, for example, or Germany. My personal opinion is that this will come at a later stage. At the moment, all the quantum computers are located in North America. So if I select West Europe here, then this just means that the providers and the workspace are based in West Europe. I could reuse an existing storage account or manually create one. I let this be created automatically. Click on Next. And then I need to specify providers. Providers are similar to printer drivers, let's say. You just specify, okay, in future, I want to submit jobs to IonQ, for example, then you would configure IonQ into your workspace. This doesn't mean that you get charged for it, just for adding it to your workspace. You will get charged only if you run algorithms and jobs on these target environments. And there are a few pre-configured. Don't worry, this doesn't cost you anything, especially because the pre-configuration includes only those providers that are actually free up to $500. And in my personal experience, I'm submitting quantum jobs once in a while, and I'm having really difficulties of spending these $500. So with simulating it beforehand and then later submitting it, you will have really a long way to go with these free offerings. So you configure these providers into your workspace and click on Next. Then let's check whether everything's good, and then click on Create, and that's basically it. Then this will take 1 or 2 minutes to get provisioned. And I don't want to dive into wait for that so that I'm going to an existing one that I'm always using for my demos. This is a quantum workspace. And you would get a similar one if you do follow these steps. There are the providers configured. Here's my quantum workspace. And if I go into that, things look very familiar. I mean, you find here the menu that you are familiar from other services, which do exactly the same thing like with the other services. The interesting part is here the notebook experience. We integrated the capability of running Jupyter notebooks in the Azure portal. And this means that you don't have to configure anything on your local PC. If you just want to play around, want to get some experience with quantum algorithm, want to submit smaller jobs, then you can absolutely do that in the portal. I would say it's built for playing around with the service, getting experience. The drawback is that you don't have version control or things like that. If you want that, then use other tools like Visual Studio Code and version your code with GitHub or whatever. But for getting started, this is absolutely a great way of getting started. And you see here, there are already samples configured. There's a sample gallery. And if you want to play around with the quantum service and use famous algorithms like Grover search or Deutsch-Joscha, for example, click on copy to my notebooks, and then you can run these notebooks. And these notebooks typically, let's go into Grover search for a second. There's a lot of documentation involved next to the actual code that gets submitted to the target environment. So it's a very easy way of getting started with Azure Quantum. Here under job management, you see what job have run on Azure Quantum. Here you get an overview of the providers that are configured. And here under credits and quotas, you see, okay, how much money do I have left on my quota? And you see here, yeah, even I have not used very much, yeah, even though I'm working on a regular basis with these environments. So much for the demo for the moment. And now you're wondering, how would I now create a quantum algorithm, and how would I then write something that is executable on a quantum system? Remember, we said that a quantum algorithm on a very high abstraction level has these three phases: initialization phase, state evolution, and then a measurement at the end. And this is basically what you are specifying when you write an Azure a quantum algorithm, not only for Azure Quantum, but for any quantum system. You specify how many qubits you want, for example, how the state evolution should happen, and then at the end, you would specify what of these qubits get measured. The way of specifying a quantum algorithm depends a bit on the flavor of quantum computing that you are working with. In Azure Quantum, we support two basic flavors of quantum computing. The first one is the quantum computing in a narrower sense. And if people talk about quantum computing, in many cases, they mean this flavor of quantum computing. This is the so-called gate-based universal quantum computing. In this flavor, you actually work with qubit. You specify a gate circuit, meaning that you specify each step very individually. This is the most important or most powerful way of doing quantum computing, because you have influence on every single step that happens on the quantum computer later. There's a second flavor, and if you go to the literature, there's a third one, which is quantum simulation. This will come to Azure as well. But the second flavor here is the quantum optimization, and some companies call it annealing, or this is what other companies might mean when they say, okay, quantum annealing. We call it quantum-inspired optimization. And there also quantum effects are used to do this state evolution. But the quantum effects that are used there, our researchers found out that these effects can be effectively and efficiently simulated on classical hardware. So if you use the quantum optimization path on Azure Quantum, that at the end, your quantum algorithms will be executed on classical hardware. It will be virtual machines and all that stuff. You don't have to care about that. It's just important to know there are no qubits, actually physical qubits involved, but classical IT that simulates quantum effects, and it does it efficiently. So don't worry, you don't need these qubits in that space. But the main difference from a programmer's perspective is that in that flavor or path, you don't specify a gate circuit, but a cost function. And this cost function specifies in what state the quantum system gets initialized. And then the state evolution is done basically automatically by choosing a so-called quantum solver or optimization solver. And we have a couple of them available in Azure Quantum. And depending on what solver you use, the state evolution is happening in a different way. But at the end, there's a measurement happening and you get a result. Let's have a look at these both flavors. First, quantum computing, and then we have a look at quantum optimization. So in the universal quantum computing, you specify a gate circuit. And what you see here on the right side on this slide, you see probably the most simple algorithm that you can imagine. It's an algorithm to create a random bit. And even if in this little program, you see these three phases. You see the initialization, which is the thing that you see here in this command here, use qubit. So you specify that you want to have 1 qubit you're working with. Then you apply a gate on that qubit, which is the H gate. This is the so-called Hadamard gate, and this puts the qubit, which is initialized in the 0 state, in a perfect superposition. That means that these two coefficients, alpha and beta, have the same value, which means that if you measure that qubit, then at the end you get a perfectly random result, 0 or 1. And the measurement is done here at the end. If you are a .NET developer, then you can also read the rest of the code, or if you're a Java developer, it looks probably also familiar. You have namespaces here that you include because you're using some functions of these namespaces or libraries. You specify a namespace for the program itself, and yeah, that's basically it. So this is a basic program, and this is something that you can actually submit as a quantum job to a quantum hardware. And let's have a look at how this looks in a working environment. I have the same program here that you saw on the screen loaded in Visual Studio Code. So here the qubit, the Hadamard gate, and the measurement at the end. What's a little bit different is I have a second function here, and the second function here uses the first one to not just create one single random bit, but a random integer. And you can specify in what range this random number should be. So it calls the random number generator a couple of times until it gets a value that is of the required size. To run this program, I can just type in, first I need to go to the directory, .NET run. I need to specify the max parameter here and say, for example, create a random number between 0 and 100. And I'm running this now on the local simulator. And since I only require 1 qubit here, which is repeatedly used, I can absolutely simulate this program on my local machine. I mean, later when I run it on a quantum computer, it's a different story, but this is absolutely running locally here. If I run it again, I should get a different number. And since Q# is a .NET language, I can very easily integrate that in classical IT. And why would I do that? It's because, of course, if you are a quantum scientist or data scientist, you want to play around with Jupyter notebooks and experiment a lot with quantum hardware and so on. But at some stage, you probably want to offer this functionality to colleagues or customers or whoever. So you would need a classical way that those people then can call your functionality, and this can be an API or whatever. And what I've done here is I added to this solution a C# program, and the C# program just includes the library that is generated by the Q# compiler by using this statement here, using hello random number service. This is the namespace that I specified here. So I can very easily call this service here. So if I go to the other directory, now I'm running my C# program, and I'm using the C# program to create a little user interface in form of a question that I'm getting asked, what's the maximum number here, for example. I could do this in Q# as well, of course, but for the sake of illustration, I have coded this in C#, and I could say, okay, let's make it 20, and then the Q# program is called, and it says the random number generated is 7. This can be absolutely an ASP.NET application. It can be an Azure function, for example, so it can be called via an API, and how this looks, we'll have a look at later. So let's get back to the presentation, and let's have a look at the optimization part. The optimization, as I said, is a little different in the way it works and how you would code for that path. Optimization in general is the challenge of finding a configuration from a huge selection of options that minimizes a certain cost. And you specify the problem domain by creating a cost function, and a cost function could be something that is here illustrated by this graph here. So the challenge would be to not only find a local minimum, but the global minimum, for example. And this is one challenge in optimization solutions, that you get stuck in one of those local minima, for example, in the one here, so that I mean, there are algorithms like gradient descent where you just start at a random point and then you look around at if you find a point lower than your own, then you go to that point and restart the whole process. But if you end up in local minimum, this algorithm will not be able to find out of this valley here. So there are quantum effects like thermal jump in annealing or quantum tunneling that uses quantum effects to find a lower minimum or a lower valley, for example. The thermal jump allows the algorithm to jump over hills that are next to your minimum, for example. Quantum tunneling allows you to tunnel through hills to get to a lower minimum. And it turns out our research showed that these are two quantum effects that can be efficiently and effectively simulated on classical hardware. That's why if you're going through the optimization path in Azure Quantum, you actually run your algorithms on classical hardware. So you're wondering what are problems that are very well suited for QIO, for the quantum-inspired optimization. If you have a single smooth landscape, then of your cost function, then your classical algorithms probably will lead you to a solution very efficiently. So the using quantum effects won't bring you an advantage. On the other hand, if it's more or less completely random and it's very scattered, then also quantum effects won't bring you an advantage because it's too chaotic. The optimum solution or the optimum problem domain is the one where you have a structured rugged landscape where you have lots of hills and valleys and so on, but it's a little bit smoother than in the complete random way. So this would be a problem domain that is very well suited for that. So if you specify an algorithm for a quantum-inspired optimization path, there you formulate a so-called cost function. The cost function here on the right side, you see a Python script that includes a couple of namespaces here or elements from namespaces. It connects to the quantum workspace, and then it defines a cost function. And the cost function in this example is C equals minus 9x0 minus 3x0 x1 plus 5x x0 x2, which is not a very complicated cost function. In reality, the interesting cost functions are those who have like 10,000, 20,000 of these parameters. And the art of developing an algorithm or solving problems on Azure QIO is to create this type of cost functions. We have some guidance, we have some documentation that shows you how you would, for example, in like risk management domain or like job scheduling problems, how you could derive a cost function. And this cost function here is very simple, just to make it easy to comprehend during the presentation, consists of 3 terms, minus 9x0 and so on. And these terms are represented here in code. This is very easy, so you would be able to solve this problem here in head, or at least with a little piece of paper, and you just go through all alternatives. But as said, the real challenge is solving cost functions that have 10,000 of these parameters. And the challenge or the task for the optimization solver is to assign values of +1 or -1 if it's an icing problem, or a 0 and 1. And let's have a look at how this looks like in Azure Quantum. And let's get back to the portal. And here in the portal, I showed you that we have an integrated notebook experience. And as said, you can load here a couple of demos, or if we go to the optimization space, optimization solutions. What I did, I created a Jupyter notebook that actually implements the sample that I just showed you. Yeah, it's the one that connects to the workspace. Let's just do that here, execute this cell. Then I define the problem statement or the cost function here. I execute that as well. And then I send the whole thing to a quantum optimization solver. And in this demo environment, I'm using a parallel tempering solver. There are a couple of different ones. It would be a bit too complex to explain the difference between those optimization solvers. But if I submit then the problem to a solver, I get a result. And then let's just print the result. We see it here. And the configuration I'm getting back are the values that are assigned to the different parameters that I have in my cost function. So x0 should be set to 1, x1 should be set to 1, and x2 should be set to -1. And in that case, the cost functions gets minimized. So this all seems to be a bit abstract. I mean, cost functions, where do I get this from? And this might not give you an actual idea of what problems are suitable for a quantum-inspired optimization. And for answering the question, what problems are suitable for quantum computing, I happily reference this study that our colleagues from McKinsey created. And here's the link to this study. And the guys from McKinsey, they also differentiate between the so-called annealing and the gate-based quantum computing. These are the 2 flavors that are available in Azure Quantum as well. And they say, okay, for gate-based quantum computers, Early stage, this is where we are right now, or maybe somewhere in between early and late stage, where we have about 100 qubits. This is the current size of commercially available quantum computers today. And here you see typical problems that can be solved with the quantum computers that we have today. And the 10,000 is more or less, yeah, what you get with this optimization approach. And here you see today what you can do with quantum computers is create random numbers, certified randomness, because quantum computers can create actual random numbers. It's not pseudo-random. What you have with classical IT is perfectly random. Or job scheduling optimization, route and fleet optimization, for example. These are challenges that you can address with current environments. At late stage, you get more options here, what is possible. And then if we come to really large scale quantum computers in, let's say, 5-6 years time horizon, then a lot more gets possible. So this is really a great study they did and a great summary, and it's really worth having a look at that to get inspired what actually quantum computing can be used for. The process for creating a quantum program or a quantum algorithm can be split into these phases. You first build your quantum algorithm, you choose your language, the tools that you more or less want. We support Visual Studio Code, Visual Studio, Jupyter Notebooks, other Jupyter environments. So depending on where you come from, you can use Q#, Qiskit, Cirq, do your programming. And using QDK libraries, we have libraries that already bring you functionality that otherwise would be very hard to implement yourself again. Like there's chemistry library, for example, for chemistry simulation that you can use these for. Then you have an integration phase. The integration phase means that you integrate your quantum solution in a larger context, because in most cases, you don't want to only implement a quantum algorithm or a quantum program, but make it available to other components. For example, if you have a job scheduling algorithm that runs on Azure Quantum, then you might want to offer that functionality to a job management program, for example, where you have data about, or where you generate data about the jobs that need to be performed, completed, and then submit the whole thing to the quantum process, and the quantum process then gives you back the result, and then you want to visualize or print out the result or whatever. Integration also means that you integrate it in other Azure services. Like I said, Azure Functions, for example, to offer a certain functionality as an API, for example, which I'm about to show you in a moment. Then testing is very important, not because testing is important in general. I mean, in the classical IT, testing is important as well. In the quantum space, there are additional challenges because, as I said, you cannot look at the actual state of qubits. If you debug through your quantum algorithm, you cannot look at a qubit on a quantum hardware and look if it behaves like you intended to behave. In many cases, you will only see at the very end if the result is the one that you wanted to have. So it's important to simulate first, to see on classical hardware whether the algorithm is doing what you want it to do. Then maybe you want to make resource estimation. This is another functionality included in the quantum development kit, which tells you how many qubits you will need on an actual quantum computer if you run your algorithm locally on your local environment. And then at the last stage, you run your code on actual quantum hardware. One thing I want to show you is a solution I built for illustrating how to offer quantum functionality via an API. This is a little program I coded to solve the traveling salesperson problem. This is a problem that has NP completeness complexity, meaning, I mean, many of you know the problem. It's the challenge of finding a path through a number of giving destinations where you want to visit each destination only once, and at the end you want to visit all, and you want to do a round trip through these locations. And with the growing number of destinations, the resource requirements to calculate the optimum path grows exponentially. And that's why using quantum-inspired optimization can bring you a benefit here. So I have a function that that provides an API and lets me call the quantum component. In my case, what I haven't illustrated here in the diagram, I added also Azure Maps to the whole thing, because we have a reference implementation for the traveling salesperson problem, but this reference implementation requires you to specify latitude and longitude of your destinations, and in only very rare cases you have that at hand. You might have physical addresses of destinations you want to visit. And to show you how this is looking like here, let's go to Postman. And Postman will call my quantum algorithm. And what I have here in the body, I have a specification of destinations I would like to visit. And in this example, these destinations are the Microsoft offices in Germany, for example. So if our CEO wanted to visit all these destinations and start in Munich, where our headquarter, our German headquarter is, then the question is, okay, in what order should he or she visit these? You can optimize by travel time or by distance. The funny thing is actually that optimizing by travel time will give you a different order than by distance because of traffic conditions and so on. So if I submit this, Azure Maps will be called to determine longitude and latitude to find out what these points are, and then submit another JSON file to the Azure Quantum service, and the Quantum service then returns a recommended way. This will take a few seconds. It's always the Azure functions are slower than the quantum component. It will appear in a second. And this is just one example. I mean, you could imagine having ship loading, for example, which is the challenge of distributing containers of different weights onto a finite number of ships, for example, so that every ship has this more or less the same load. Here we have, let's make it a little bit more nicer to look at. You see here the suggested order is to start in Munich, fly to Berlin, then Hamburg, Cologne, Frankfurt, Waldorf, Stuttgart, and Munich. Interesting enough, I did this thing yesterday, and there was the order in the other direction. It's probably a weekend a phenomenon that it's faster going first to Berlin and then going through the other offices. So you get an ordered list of destinations back. So this is an example how you would use quantum in classical components as well, because this function here now can be called from an ERP system, for example, or a traveling management system where you want to plan a journey and want to visit these locations and wonder what direction you should go. So let me come to the end. As summary, I showed you why we need a new way of computing. It's because there are challenges that have, or compute challenges that have a complexity that we cannot and will not be able to solve with classical IT because of their complexity. And their quantum approaches can help you to solve these problems. So it's not a question of waiting until classical IT is available to solve these problems. These aren't solvable in the classical way. So that's why we need a new way of computing. And with quantum, we write algorithms a little bit differently, like we do it in classical IT. In quantum, we describe an initialization, we describe how this system should evolve over time, and then we measure at the end. And we do the specification of these algorithms by either using Q#, for example, to specify the gate circuit, or use Python, for example, to describe a cost function that should be solved by an optimization solver. Azure Quantum is available more or less for free. I mean, if you want to play around, get an Azure free account, which is available for 12 months, where you have already Azure credit. And then you have Azure Quantum credits to run your algorithms, test it, play around with it, get some experience. And the family of quantum hardware is growing and growing. I mean, we recently announced that Pascal will join the family of quantum hardware. There will be other environments available in near future as well. So use it. You don't have to pay anything. Play around, get some experience, prepare yourself for a quantum future where larger scale systems are available, and then other challenges are also tractable. Enterprise Acceleration Program, if you are an enterprise customer, this is for you, then we can work together. Here are a few links. I think we'll make the presentation available later where you can click on the links there to get additional information. One of my favorites is here, the Quantum Katas. This is a collection of Jupyter notebooks where there's a lot of documentation next to the actual code that can be executed. We have Q# code samples, we have samples for the optimization path, and so on. Just use these resources to prepare yourself for a quantum future. And if you have additional questions, just contact me on LinkedIn or wherever, and I'm happy to help you and prepare you for a quantum future. Thank you.